So starting chapter 5, this is called Transcendentals, and really it's just because we're going to be doing both derivatives and integration with functions that are a little bit more complicated than just trig or polynomials. So like you see here that we're going to be dealing with natural log. For the most part, almost everything I do today, I've already taught you in December. So this is going to be the second time you've seen it. You probably will remember some of it, but maybe not remember all of it. But I'm going to kind of teach it as if it's the first time you've seen it. Okay, so if you're like, I don't remember any of it, it'll be all right. All right, now, this right here is the basic rule of how we take the antiderivative, right? We add 1 to the power, and then this says divide by, but it's like writing the reciprocal in front. Okay? There is an important disclaimer. It does not work with a problem like this. Because think about what would happen here. We'd leave a space, we'd write the x, and then what would be the new power? 0. And so what would you write here? Maybe 1 over 0? And that is not a number. Okay? This does not work. So we're going to have to bring in natural log to explain this. All right? The natural logarithm is defined by this equation. Okay, now that you know what an integration symbol is, this hopefully makes sense. A natural log of a number, okay, which before you just typed in your calculator or was like e to some power, all of that is the same thing as the area under the curve of the rational function. That's what it is by definition. Okay, you didn't know this before. You just knew that logs have to do with exponents and their inverses and all that. So the reason this is important is because this is how we're going to get our derivative. Okay, we're going to take the derivative of the left side, and that's going to equal the derivative of the right side. Now again, how do you derive an integral? Second fundamental theorem of calculus. So you're going to see a few different applications of this. So remember that you plug in the upper bound, okay, times the derivative of the upper bound, minus, plug in the lower bound, times the derivative of the lower bound, and what does that all simplify to? One over x, right? 1 over x times 1 minus something times 0. This right here is the derivative of natural log. Okay, and again, I taught you this in December, but I didn't really teach you why. I just said, hey, this is something you need to know now. The derivative of natural log of x is 1 over x. Now, sometimes, though, we're not going to be deriving just plain natural log. Look at this example down here already. So what we're going to be doing, is taking natural log and taking the derivative of something more complicated. So do y'all remember in general how this goes? Anybody? Yeah, it's like the derivative of u prime, goes in the numerator, and just regular u goes in the denominator. And now we even know more about u. We know that u represents something like an expression in terms of x. Okay? So I'm going to go ahead and do problem 1, then we're going to finish these notes, and then we're going to do the other problems. But I want to really kind of just get this out of the way right here. When you're taking derivative of natural log of something, okay, it is a fraction. In the numerator, you write the derivative of that, what we call the log argument. In the denominator, it is that thing exactly. That's how you take derivative of natural log. And this is something that, once you kind of understand the rule, students tend to do very well on. Now, some problems tend to be a little bit harder. And what I want to do is kind of go over some properties of logs, and some of these we'll discuss now, and some of these we'll discuss on the back, okay? But let's just talk about them, get them all written out down. So what is the domain of the natural log? Anybody know? If you draw a picture of it, it may be helpful. So that is not a straight line. Well, it's a straight line, it's not a vertical line. Okay, there we go. Whoops. Oh, wrong way. Okay, there's my axes. there's natural log, or really any log looks about like this, and that's the point 1, 0. So there is a asymptote at x equals 0. And so the whole graph is to the right of that. So what would the domain be? So 1 to infinity would be from this point on. But I have a graph over here.
0.
Yeah, and I know some of you just said this a minute ago. What about the range, bottom to top? All real numbers, which you can write this way or with the r symbol. Okay, a couple things we know. We know this function is continuous. This is good. This means we get to use all of our favorite theorems. Okay, increasing. That means that the first derivative is positive. All right, we can see that it's increasing. And here's the deal. When our domain is only positive numbers, doesn't it make sense that this thing, which is the derivative, is always positive? All right, so then what about concave down? What does that mean? That double prime is negative. So if I were to take the derivative of 1 over x, and I were to plug in any positive number, it would give me a negative number in here. Okay, I didn't say anything about this 1-to-1. Really what that just means is for every x, there's one y value. That's what just being a function is. But it also works the other way. For every y, there's only one. So 1-to-1 means that it's not going to go up and down and up and down. It's just constantly increasing. Okay, look at these properties over here. These are some other log properties. Natural log of e equals a number. Anybody know what it equals? 1. Very good. What about natural log of 1? 0. Yay. 0. So what about a property about natural log of a times b? It's natural log of a plus natural log of b. This is going to be important later when I'm trying to take the derivative of something. I can split it up, and instead of having one giant problem, I can have two simpler problems. Okay, what about number 4? Yeah, move that n down to be a coefficient. Number 5, natural log of a minus natural log of b. So very similar to 3. And then if you combine 1 and 4, you get 6. So what's natural log of e to the power of n? Just n. Good. And so this really helps us kind of, if we use these properties wisely, we end up doing less algebra later on. Okay, so let's kind of go through the rest of these derivatives, and we'll use some of the properties now, and some of them we'll use on the next page. And so looking at 2, is there anybody thinking, hey, move that x to be the power right here? Anybody thinking that? Or not? Do you know how to take the derivative of that? Neither do I. So we're not going to do that. Maybe you aren't thinking it. I don't know. Okay, but what we do need to do is deal with the fact that there's two groups. So I'm going to have to use product rule here. So remember, a product rule is derivative of the first thing times just the second thing plus just the first thing times derivative of the second thing. We're going to review a lot today. What does this second part simplify to? 1. You don't have to write that. The reason I bring it up is if we're going to use the derivative for something, it may be beneficial for you to simplify there. We'll worry about that on the next page. Okay, look at number 3. Can I use property 4 up here on this example? Can I use this property?
No, because it's cubing the whole.
Yeah, number 3 is saying you're cubing the whole thing. You're not just cubing the x. So I can't use that property. But I can still use, I keep putting little dots everywhere. It's bothering me. All right, but I can still use a rule, chain rule, the M&M. Take derivative of the shell. So the 3 is being moved, but not because of that log property. It's different. It's being moved because I'm deriving the cubed part. So you leave natural log x alone initially, then you go times derivative of natural log of x, which you just need to know is 1 over x. And that is the answer. Okay, number 4, we can use one of these properties because this x plus 1 is being taken to a power. What power? 1/2. And so that 1/2 can be moved to the front. Now let's say you just totally didn't know this. You didn't do this property and you still just went on with the problem. Your answer, if you did it right, would be the same as mine, equivalent, I mean, but you would do a little bit more work to get your answer. So it's always going to be to your benefit to use these log properties. Okay, so if you're like, what do I do with the 1/2? Just write it and write a time sign. Okay, a fraction for natural log of x over 1. Remember, the derivative of x over 1 goes on top, and x plus 1 itself goes on the denominator. And that is your answer. Okay, look at number 5, absolute value bars. That's weird. That wasn't on any of the other ones. Why do you think there are absolute value bars there anyway? Like, what is an absolute value? Sine is cosine, well, sine also is positive and negative, right? And we can only take natural log of positive numbers. So that's why there's absolute value bars here. It's really not going to affect our problem. And you may be thinking, well, why weren't they on the other problems? Right? Well, look at number 1. X squared plus 3. Isn't that already always positive? A square root. Square roots are always positive. Okay? Now, if you look at the other ones, you kind of have a harder time justifying it, except that they probably implied here that all x, just x, is positive. So don't let this freak you out, okay? We'll talk more about the whole absolute value thing tomorrow, but for now, we'll just pretend that these are parentheses. All right, so the derivative of that goes on the top, negative sine x. Don't take away the negative because you saw absolute values, okay? All right, and then that thing itself goes in the denominator. This is your answer. If this was multiple choice, it might be possible this is written a slightly different way as negative tan x. That's not something I'm expecting you to do, but it's something that you need to know. Like, if your answer's not there, think, well, is there an answer that's equivalent? Okay, look at number 6. Number 6 is screaming. It is screaming, use the log properties. You hear it? Okay, how many groups of log, after we expand this out, how many groups are we going to have?
2.
I see an x, and I see something squared, and I see a square root. So I actually see 3. Okay, this x right here, that's going to be my first group. All right, see the second part? It's on the numerator. So all right, plus. See the squared? That's going to become the coefficient. I'm using lots of log properties here. And what do you think is the last part? Minus.
4x squared.
Mm-hmm. What's going to be the coefficient?
Negative 1.
Exactly.
Oh,
You can think of it as a negative 1/2, or you can think of it as minus because we're in the denominator 1/2, but there's not 2 negatives there. All right, now that's not my answer. That's really just prep work. I still got to take derivative of each of these things. So the derivative of the first piece, that's just 1 over x. And again, with this whole 2 times, don't let that throw you off. It's just 2 times whatever the derivative of the natural log is. Numbers, don't sweat the numbers. What would the numerator be on the last piece? That's right, 8x. I know I'm a little ahead of y'all. Okay, any questions so far? Any of this come back, seem familiar after we've started it? That's good.
With the In between the 1/2 and the, no, should that be plus 1/2 or?
This should be minus because it is in the denominator. Or you could think of it as the power on this is a negative 1/2 power.
Oh, I think I got confused because like we put it as -1, but I was thinking it was the denominator, so we have to like subtract.
No, what I did here is good. Okay, turn the page over and we're going to apply this on a few different types of applications. And again, lots of review. Okay, so hang with me on this. If you're like, don't get discouraged if you've forgotten a lot of it. Just be like, I'm glad we're reviewing it then. Okay, relative extrema. What do we need to do first? What did we do at the beginning of pretty much every problem last semester? Derive. Find the derivative. So again, it's a fraction. The derivative of that thing goes on the top. That thing itself goes on the bottom. Okay, now, relative extrema would be maxes or mins. And this is where y prime could equal 0, or it could be undefined. Remember a cusp? Remember what a cusp was? The derivative was undefined at a cusp, but you could still have a relative max or min at a cusp. So that's why we have to check that. All right, so with a fraction, it's not too bad because you're really just saying, where's the top equal to 0? That's the 0 part. And then if you set the bottom equal to 0, that takes care of the undefined part. Yeah?
Wait, why don't you put the 1/x?
So this was back to the, so with the derivative, I'm looking at this thing right here, and I'm using the fact that it's more than just an x. I put the derivative of this on the top, and I put this exact thing on the bottom. It's like u prime over u. So the whole 1/x piece, you really only do that when all you're taking natural log of is just x. Good question. Okay, so set the top equal to 0. 2x plus 2 equals 0. What does x equal? -1. These are called critical numbers. These are possible maxes and mins. All right, so the bottom equal to 0. Again, this is figuring out where is this derivative undefined. Okay, how do you solve that? Factor. Okay, try to factor it. Some of you on the last after party kind of messed up because you made something factor that wasn't factorable. Not everything factors. And this is one that doesn't. It looks like it should because of like the 3 and the 2. If there are minus signs or plus signs, or if the 3 and 2 were switched, this would factor. But it doesn't factor. So guess what we get to do? Quadratic formula. Now watch this. There's going to be good news. Don't get too discouraged here. Watch what's going to happen. And this is what's going to happen, not every time you have to do quadratic formula, but a lot of the time, if not most of the time. You do quadratic formula and you find out that the result has a special property. What do you think? Look underneath the square root. Yeah, 2 squared minus 4 times 1 times 3, that's a negative number. In this class, do we square root negative numbers? No, we don't even have to say the I word.
The eyes?
We just say, we don't do that. Okay, see, there was good news. So we only have one critical number. So let's put it on a number line. And remember, what we're going to do is we're going to plug things into y1. So like really highlight that if you need to. And then that's going to tell us something about y. So if you take a number, so like, go ahead and anybody choose either side you want and test it. See if you get positive, negative, and that's going to tell you about increasing and decreasing. Remember, you don't have to really figure out what the number is, you just have to know positive or negative. Okay, so this is what I got. I got numbers on the left of -1 are negative for y1. We're plugging it into y1. Okay, so that means that my function y, my original function, is decreasing here. Okay, and I got that a number bigger than -1. Say 0 would probably be the easiest thing to plug in. That would be just 2/3 positive. So that's increasing. So I do have a relative extrema. Which one? Relative min. I can see it right here. It even looks like a min if I draw it. And that's happening at x equals -1. It doesn't ask me to explain why, but I'm going to go ahead and do that just for fun. Because really, that's so much fun. I don't know what you guys do. This is what I do. Okay, you ready? Move on to the next problem. Okay, so implicit differentiation. This should be pretty fresh on your mind because I've put this on a lot of the after parties recently. So, derivative of x squared, 2x. What's derivative of -3 natural log y? -3 times what? 1 over y times it's y, dy over dx. And remember, dy over dx is what you're going to get by itself, so you have to have it. If you don't write it, then you're going to not be able to get anywhere in the problem. Okay, plus derivative of y squared, that's going to be 2y, and again, dy over dx. Because I'm deriving with respect to x, that's why I have to do that with the y's. Okay, equals 0. Make sure you write 0 on that other side, not 10, because we're deriving. Okay, now, we need to keep the terms that have a dy over dx on the left, and we need to move the terms that don't to the other side. So I'm just going to write -2x over there. How do you get the two dy dx's into just one? Factor it out. So -3 times 1 over y plus 2y equals -x. So what would just dy over dx equal? This is the part everybody remembers, which is divide. Now, probably if this was on the AP test multiple choice, they would do something so that you don't have a fraction within a fraction. I'm really not going to focus on that in this chapter. That's something that I'm going to wait till it's closer to the AP test, and then I'll help share with you, because it's really, this answer is perfectly fine. Okay. And that's what we're focused on right now, are right answers, not simplified answers. Okay, equation of a tangent line. Everybody's favorite. We need 3 things. What are those 3 things? X, y, slope. Don't fall asleep if I gotta keep it up. I'm ready. Okay, so for the y, let's go over here, and this will be like our scratch work. So y equals 3 times 1 squared minus natural log of 1 squared. Well, that's natural log of 1. 0. So this whole thing equals 3. So my y value is 3. Remember, you just use the original function to find y. So that's where that property of knowing natural log of 1 equals 0 is really important. Alright, now to do slope, I need to do y prime. So we already practiced this several times today. Derivative is 6x. Now you could use a log property here. That would be okay. I'm gonna, for this one, just pretend we didn't see it, and you'll see it's okay if you didn't know the log property was there, because you're gonna get 2x over x squared. Remember, you just take the derivative of x squared, it goes on top, and then x squared itself goes on the bottom. This itself is not my slope. This is the derivative. This is the representation of all the slopes. But I want to find the slope at this particular x. So in order to do this, I need to plug in 1 in for x. So 1 is an easy number. It's nice. It's easy to multiply and add and all that. So what does that equal? 4. The slope is 4. And so my final answer, I know you guys are really good at this part. You don't have to get y by itself or anything like that. Okay, one more problem. You ready?
Yeah.
Woo!
Woo!
I love it.
How you guys doing tonight?
Okay, so number 10. All right, we're doing this. We're in this together. You got two things. Which thing are we going to find first? Point of inflection or relative extrema? Yeah, that's first derivative. So, all together now. Y prime. We got to use the product rule. So, derivative of x squared is 2x times just natural log of x. Remember, you're not doing derivative or derivative. Okay, plus just x squared times the derivative of natural log of x. Now, in this case, I do want to simplify because it's going to help me because I have to do something with this. So if it's simplified, it's going to make my life easier. What do I need to do with this derivative? What did we do up there on number 7? Set the derivative equal to 0. This one's not a fraction, but we're still setting it equal to 0. And we do also need to figure out whether this is undefined. And I'm going to ask you that in a minute. All right, now, this kind of gets lost on students the first time, and then they are good. This is two big terms. Do they share any factors? X. So I factor an x out. So again, this may not have been obvious, but you'll see it, and then you'll practice it and you'll get used to it. So factor just like how you did any of those other problems, and then set your two factors equal to 0. So there's one critical number right there. Another critical number, we subtract the 1 and divide the 2. Who can tell me what just x equals? I have not talked about this yet. You might remember. What's the base on that log? It's log base. So if it's log, it's base 10. But if it's ln, it's log base e. So remember when you were rewriting logs and exponents like back and forth last 2 years? You would say e to that power equals x. So again, this is kind of weird, but next time you see it, it won't seem as weird. Okay? That's what I'm focusing on here. Just exposure and getting used to seeing it. All right, so we have two critical numbers. All right, so that's when the derivative equals 0. Where's this derivative though undefined? And I'm really looking right here. What type of x values can we not have? So I'm putting my critical numbers on here. What are numbers that I cannot test because I can't even take natural log of them? Negative numbers. You cannot take natural log negative. So this is what we get to do. We get to scratch that out and be done with it. Okay. Here's the deal with this next part. I need y'all to really focus in. We just kind of threw some earlier classes for a loop. It's not that it's that hard, it's just that they weren't paying attention and they were like, what? Okay, without a calculator, we have to test numbers here and here. Probably it's going to go plus, minus, or minus, plus. So which of these two sections do you think would be easier to find a number?
0 and e.
Do you even know what this is?
No.
So maybe let's pick a number on the right side and pick like 100.
What if it's greater than 50?
That's fine. It's just any number over here.
No, I'm saying what if, well...
Oh, it's not. it's not going to be greater than 100, but that's a good point.
You never know.
So let's pick a billion.
A billion.
No, like that.
All right, so remember what we're doing here. Okay, so just think of it this way. 2 times a really big positive number times nat is a big positive number. Natural log of a positive. Remember, natural log was increasing. So if we take natural log of a positive number, we get a positive number. And then we add another positive number. Our result is positive. Okay? So what do you think this is over here? Negative. Now let me really listen to this. Okay? A tiny, like think of the tiniest number. Okay? Like 0.0001. Okay, 2 times that is still pretty small, but it's still positive, and if you add, but natural log, let me redraw the parent function for you. What is natural log of a really tiny number? Like when x is really tiny. Negative and, well,
Almost 0.
no, like when x is really close to 0, we're talking, we're like doing this.
Yeah.
So like negative,
Infinity.
it's like negative infinity basically. You could say tiny, but it's negative big really. I know, it's okay. So here's the deal. Natural log of 0.00001 is like negative 1 billion, we'll just say, okay? So this whole result is going to be negative. Now, if you had a calculator, would this process be easier? Do you know how you could use your calculator to make that process easier? Plug in your calculator, e to the negative 1/2, figure out what that is as a decimal, and go from there. You're going to get to practice that on your homework, or you can do what I did here. So we have a relative min at x equals e to the negative 1/2. It doesn't ask us to justify, and we won't do it for fun. Now, here's where everybody today has been like jumping for joy. We're only halfway done with this problem.
Yeah.
Okay, points of inflection. So for points of inflection, we need to know the second derivative. Now remember, this was my first derivative simplified. So we need to use product rule again. We're together. I'm doing this with you. Okay? Take the derivative of 2x. You get 2. Just natural log of x. Right? Plus 2x times what is the derivative of natural log of x?
1 over x.
1 over x. Plus, what's the derivative of just x? 1. Okay, look at this. Those cancel. So what does this whole thing simplify to? 2 natural log of x. 2 plus 1.
3.
Yay! Okay, equals 0, right? We've got to go through the same process. Equals 0, undefined, all that. So, natural log of x by itself, after I subtract the 3 and divide over the 2, is negative 3/2. And I told you guys this would be easier the second go round. So you got to prove me right here. What is x? Perfect. You guys are geniuses. Okay, so then that's my only what we call possible point of inflection. We need to prove that there's an actual change from positive to negative. We have to show that. Okay, because we have to show that the concavity is changing. Now, even though x equals 0 wasn't one of my answers here, I still know that x has to be a positive number, so we still get to do this. It may seem like there's not a point to it, but there is. You can't even consider negative numbers here. And that's why we talked about domain earlier. All right. So we can do the whole teensy-tiny little number. And we could do the big number, or you could use calculator. All right, due to the time, I'm going to go ahead and tell you that you get a negative here. For almost the exact same reason you get it over here. So that's concave down. We get a positive over here, concave up. So you just plug the number back into the second derivative. And again, if you had a calculator, this would be easier. So when you're doing your homework, do use the calculator. But if you feel like you could do it without, that's a good practice as well. Okay, so do we have a point of inflection after all? We do. We have a point of inflection at x equals e to the negative 3/2. You don't have to write a justification, but verbally, what's your justification? Y double prime changes signs. Okay? Y'all did good.